Hi, in this video we're going to cover searching algorithms to search lists, and we're going to start off with the sequential search. Sequential search starts at the beginning of the list and goes through the list one at a time until it either finds the item that you're looking for or runs out of items, which means it was not in the list. In a sequential search, the list does not need to be sorted. So I'm going to start off here by importing a couple of libraries, random and time. We're going to create a sequential search function here, passing in a list and item, what we're going to look for. We're going to have position is going to be equal to 0, found is going to be equal to false, and then count is going to be equal to 0. So while our position is less than the length of our list, and not found, we'll go through here and look for this. And say count plus equals 1. If a list position equals the item, then found is going to be equal to true. Else, position plus equals 1. Then all we need to do is return found. So if it goes completely through and never finds it, then found will stay false. Once it finds it, found becomes true and it drops out of the while loop. Okay. So what we're going to do now is test this. We're going to return found and count so we can do some analysis of this as we're going through here. So, okay, so now let's do our main. Create a list. It's going to be equal to an empty list right now. Number is going to be equal to an int input we're going to enter how many values we want to run through the list or through the search here, put in our list. So for x in range number, list.append x. Okay, now the reason we use our random here, we're going to do random.shuffle to mix up all the numbers in our list. Search value is going to be equal to int input enter the number to search for. We're going to start our time. So time is going to be equal to time.time. We're then going to search count is going to be equal to our sequential search function, passing in list and search value. We're then going to get our end time. And then we'll print out our results on this. So, was the value found? That's our search. How many comparisons? That's our count. And time to complete. That's our end minus start. Okay. So that should be everything that we needed here. So all you need to do is add a main on there. Now I'll go ahead and save this. And I'll have to work over to where I'm located in here. Oops, wrong place. Oops, still the wrong place. I'll find it here in a minute. Should be in here. Oh, week 6, sorry, wrong week. There we go. And this is sequential search.py. Get that saved. And then we'll run this and we'll see if I have any errors in here. Nope, enter the number of values. So I'm going to do 1,000 to start. And I'm going to look for 543. Okay. Took 51 comparisons, but the time to complete was 0.0. Well, let's run this again. I'm going to put in 100,000 numbers, and I'm going to look for 9999. Okay, that one took 21,155 comparisons, and the time to complete was almost 1,000th of a second. So one more time. And this time I'm going to put in 1,000,000. And I'm going to look for that how long it took it to deliver that. Look for is 999,999. And this time it took 0.26 seconds. Okay, so you can see that as we increase the number in here, it takes a lot longer to look for these. So, okay, so we're going to do another one. And from this one, I'm going to open up a blank file here and get rid of that one because I don't need it anymore. And this one, what we're going to do is a little bit different. And I could have used the same code here to do this, but I'm going to do it this way. This is an ordered sequential search. Import random again. And in our ordered sequential search, we need to put in both our list and the item that we're going to be looking for. We set found equal to false. We set stop equal to false. And we set count equal to 0 and position equal to 0. So now while position is less than the length of a list, and not found, and not stop. So what this one's going to do is it's going to stop when it finds the number, or finds a place for the number on here. Because on this one, we're going to have the numbers in sorted order when we do this. So count plus equals 1. This is our first comparison. If a list sub position equals item, then found is going to be equal to true. Else, if a list position is greater than our item, then we're going to stop, because since these are going to be sorted, there's no reason to go any further. And then else, position plus equals 1. Then we're going to return found and count. Okay, so in our main, our list is going to be equal to an empty list. Run through for loop for x in range 0 through 1, 2, 3, 4, 5, 6, a million, increasing 2 at a time. List dot append x, and then we'll do search and count equals ordered sequential search, passing in our list and the number we want to look for. In this case, we're going to put in 535. Print. Was the value found, and then we're going to print how many comparisons, which will be our count. And then our main. Okay. So I'm going to go ahead and get this saved. I'm going to save this as ordered sequential search.py. And we'll run this. Oh, got an error, sorry. The quote mark off right there. Run it again. So was it found? False. How many comparisons? 269. So let me switch this down here. So get on there. And we'll run this again. Oh, wait a minute. Since we're not entering the numbers, I'm going to go ahead and put in here 868, because that number should be in there. And it took 435 comparisons, and it was true. We didn't do timer on this one, but it stops sooner because of the stop up here. Once we get past it, that was the 535 that we had in there. So you can see how that works on there. This is a little bit better, but it's still ON, because the worst case scenario is it has to run all the way through the list to get to the end. So, okay, I'm going to do another one here, and this is going to be a binary search. New file here, and close this one off. So binary search it works only on sorted lists. So we're going to create a binary search method, passing in a list and item. First is going to be equal to 0. Last is going to be equal to the length of a list minus 1. Whoops. Length of a list and then minus 1. Found is going to be equal to false. And count is going to be equal to 0. So now, while first is less than or equal to last and not found, count plus equals 1. That's going to be keeping track of how many comparisons we make on here. Now, notice on here, what we're doing is we're keeping track of the locations in the list of where we're looking in this. Right now, we're looking through the whole list, which is first through or 0 through the length of our list minus 1. So now we're going to find the midpoint of this. It's going to be first plus last, integer division 2, and then we're going to check to see if a list midpoint equals item, found equals true. Else, if item is less than A list midpoint, then last equals get this right here, midpoint minus 1. So that means if our item is less than this, no bracket on that. If the item is less than our midpoint, we know that it can't be greater than that. So we can discard all those numbers and just go to the numbers that are at the end here. Else, yeah, okay, we got that. Yeah, so else first equals midpoint plus 1 on there. Okay. So this means then that it's not equal right here. It's not less than, so it's got to be greater than. So we move our first point up past midpoint because it's got to be in those upper numbers. Okay, so then we're going to print count there and return. We could return count, but we're just going to do it this way. Okay, then in our main, list is going to be equal to a bracket and bracket. For count in range, I'm going to do a million again. So on 0, 0, 0, 0, 0, 0. List dot append count. Whoops. And then we're just going to print out the information here. We're going to do it. Look for find 248. Binary search list 248. Then we're going to print find 499. Binary search list 499. And then we're going to print find 1001. Binary search list 1001. Okay. And then our main. So I'm going to save this as a binary search. BY, PY, and my Y in there. Go. And then we'll go ahead and run this. Oops, sorry, I got the error in there, misspelled append. And yeah, midpoint item, not items there. Got any other errors in here? Oh, there we go. So count was 19, found 248 was true, count was 20 on the next one, find 499 was true, and count is 18, and find 1001 was true. Notice the highest one was 20, and even with a million numbers, it only took 20 comparisons to find that. Okay, if we were doing this with the either the two sequentials, it would have taken 248 to find 248, 499 to find that, and 1001 to find that. So this is a lot better searching routine than the other one. Now the last one we're going to do is a recursive binary search, and I'm just going to use this as and modify it. I'm just going to put an R on the front of this. R binary search, and I don't need this stuff in here. I'm going to delete this stuff out of here. What I'm going to put in here is if length of a list equals 0. And then what we're going to do here is return false and count. So I'm also going to have count up in here. Okay. Then I'm going to have an else here. And let's take out the while part on this. Okay. Else that midpoint equals length of a list. Integer division 2. If a list midpoint equals our item, then we return true. And count. Else, if item is less than a list midpoint, we're going to return our binary search a list colon midpoint comma item comma count else we're going to return our binary search a list midpoint colon, oh, I'm sorry, midpoint plus 1 colon item count. Okay. Then we take these two lines out of here because we already got our returns in there and we're returning the count. So then down here in main, I'm going to do for count million, do that. And then I'm going to go ahead and I'll leave those in there because I'm going to use those. Count equals 0. Found count equals our binary search list 2480 count. Okay. Then we're going to print find 248 and we're going to do found count, and then I'm going to copy and paste this. Do these two lines down here. Get rid of these two down here because we'll replace those two. And then this time we're going to do, oh, it should be 2480. And then this one down here we're going to do, we're going to find 500,000. Okay. We're going to do this again, and this time it's going to be 1001 and 1001. Whoops. Okay, let's see what happens with this. I'm going to save this. And okay, so there's find 2480. to get all this stuff in here because it kind of shows you the numbers as it went through here, or how many it took to do. Okay, so that one took 20. This one took 22 on here. So it's not a whole lot faster than the other one. It's about the same, but just to give you a comparison on between a recursive and a non-recursive one on there. So I hope you got something out of these. So thanks for watching. Bye.